Hello, thank you very much for the invitation and to the organizers for this wonderful conference. So today I'll tell you a story about moduli spaces in heterotic string theory. This is work that I've been doing over the last several years with these people. I mean, Eric Svans and Ed Hardy, Magdalena Larfors, Philip Candelas, Jock McCorrest, Marc-Antoine Fisset, Ashmore, Minassian, Strickland Constable, and McGill. I'll tell you mostly about the work in the third line with Magdalena and Eric and with McGill here. So the general context of this work has to do with the interest in effective field theory derived from compactifications of heterotic string theories and the conformal field theories related to this, when we preserve the minimum possible amount of supersymmetry. So we're interested in at most one supersymmetry. So, and of course, and what are the mathematical structures encountered? So we have the following mathematical objects in these theories. So suppose Y is a d-dimensional Riemannian manifold and B a vector bundle on Y. Then, being a Riemannian manifold, you will have a metric. We'll have a dilaton. We have gauge fields A for the gauge group G contained in the 8 cross 8. So V is a vector bundle on Y with connection A with structure group G contained in the 8 cross 8, right? And we also have a three-form H, normally called the flux, which for the purposes today is defined by this equation here. So H is, this CSA is the Chern-Simons form for A, and similar for theta, where theta is a connection on the tangent bundle, and B is the B field, so-called B field. And notice that I don't want to get into this. I mean, this is something that was explained by Wilhelm a long time ago. So B is, even though we call it a two-form, it isn't, right? It's not gauge invariant. I mean, the Chern-Simons forms do not transform trivially under gauge transformations. And so B transforms in a way that compensates for that, so that H is in fact a three-form. So what we have is a quadruple, right? We have a manifold, a bundle with connection, the tangent bundle with its connection, and the flux. So mathematically, supersymmetry will constrain this geometry, right? And I'm going to call these geometries heterotic G structures. And I will explain what they are. And we want to study the geometry and quantum moduli space of these compactifications, including, of course, we want the quantum theory. We want to include alpha prime corrections and non-perturbative corrections. And the goal, of course, in physics will be to construct the quantum effective field theory, and this is largely, to some extent, at least determined by the geometry of, and moduli of these compactifications. Right, so for example, we want to find at least a massless spectrum, the effective 3- or 4-dimensional Lagrangian correlation functions, and to study dualities, etc. Today, I will focus on the case for d equals to 7, because it's harder, right? But mainly on the supergravity side. So one reason is that the 6-dimensional case can be deduced from this. So 6-dimensional case leads to n equals to 1 theories in four dimensions, and the case d equals to 7 leads to n equals to 1 supergravity plus Yang-Mills on ADS3 or three-dimensional Minkowski, right? And much less is known about these theories. Another interesting reason is that you can decompactify one of these dimensions and go to the 4-dimensional theory, and this leads to theories with half supersymmetry. So there are really minimal amounts of supersymmetry. So recall that compactifications to 4 dimensions with n equals to 1 supersymmetry give strong constraints on the geometry already. The geometry of the moduli space. And in particular, the moduli space, for example, should be, so as an example, must be complex and Kähler. Compactifications to 3 dimensions with n equals to 1 supersymmetry are not as constrained, and we know much less about the geometry of these moduli spaces. So I will tell you what is the heterotic, what's called the heterotic G2 system, which corresponds to the 7-dimensional case. And then I'll tell you a little bit about the infinitesimal deformations of this system. And then I will, time permitting, I'll tell you a bit about the outlook and open problems. So this is for those of you that are more familiar with the four-dimensional case, this is the analog of the whole Strominger system that was discussed in 1986 by Strominger and Hall independently. And of course, in that case, we also studied the moduli space for the whole system and so on. And we, in fact, have made more progress in that case. But I wanted to tell you about this one because it has, I find it rather interesting, this work in 3 dimensions. So I will tell you what the main ideas are and a bit of the results, even before telling you what a heterotic system is. I mean, just think about this as this quadruple constraint such that you preserve one supersymmetry, right? So the conditions, what we are going to see is that the conditions for this geometry to admit a heterotic structure, that means so that you have an n equals to 1 supersymmetric theory in 3 dimensions, is equivalent, so these conditions are equivalent to a differential D that satisfies a condition so that when you do a certain projection of this operator and you square it, then you get 0. Right, so this projection is I will see what this is later. And this operator acts on forms with values in a bundle, which is a bundle on Y, I'm calling Q, which is topologically the tangent bundle plus the endomorphisms of the tangent bundle plus the endomorphisms of V. We will see that infinitesimal moduli of the heterotic structure correspond to classes in H1 of this operator, right? And we will see that it is finite dimensional. So, I mean, this is about all I will have time to tell you about. I mean, there are a number of questions that arise from this. I mean, what does it mean to ask about Morey-Cartan equations? What happens to when you deform beyond infinitesimal deformations? What is the true moduli space, right? When you include quantum corrections, what are the singularities? What happens there, and so on. So this I have very little to say for the G2 case. So supersymmetry requires that Y has, so let me start with Y, with the manifold itself. So it requires that Y has an integrable G2 structure. Now, so a G2 structure, a manifold with a G2 structure is a 7-dimensional manifold Y, which admits a smooth, non-degenerative 3-form phi, right? So if you have a Riemannian manifold, your structure group, you know, should be is contained in SO7. When you require that you have a 3-form, a non-degenerate 3-form, then that reduces further to G2, right? And this comes from supersymmetry, right? That you can construct this 3-form using a spinor, right? Abelian spinors as usual. So this 3-form determines a Riemannian metric and a 4-form, which is Hodge dual to the 3-form. Now, the geometry of Y, right, let's consider a little bit more the geometry of Y. So consider the exterior derivative of these forms, the 3-form and the 4-form, which can be decomposed into irreducible G2 representations. Right, so the exterior derivative of phi has 35 components because it's a 4-form, and it decomposes into a singlet 7 and a 27. So these terms just reflect that decomposition. And similarly for the exterior derivative of the 4-form, which decomposes into a 7 and a 14. And these taus are known as the torsion classes and are determined uniquely by the G2 structure. We call a G2 structure integrable if tau 2, this object here, is 0. And the reason it's being called integrable will become clear in a moment. So we can rewrite these structure equations for the manifold when tau 2 is 0 compactly in this way, right? So this is an insertion operator. It doesn't matter. It just means that you think of this 3-form T. You take this 3-form T, and then you contract one index of the 3-form with phi or psi. That's what this is. And this T contains the torsion classes, right, that we had in the previous slide. One can check first that if this T is 0, then all the torsion classes, tau2 was already 0, so all the torsion classes are 0 because these vanish independently because they're in different irreducible representations of G2. So and in this case, you end up with a manifold with G2 holonomy, right, which is analogous to a Calabi-Yau manifold in 6 dimensions, right? So this T here, I'm going to call it the torsion, right? And is the unique, is the torsion of the unique connection compatible with the integrable G2 structure, right? Meaning this, which is totally antisymmetric, right? It's a 3-form. Okay, so the question I'm going to ask now is that is there a differential that I'm going to call the check, so that squares to 0 and which encodes this geometry? So this is, is there an analog in 7 dimensions with a G2 structure of the Dolbeault differential del bar that squares to 0 for a complex manifold X with complex structure J? And the answer is yes, right? So we have the canonical G2 cohomology that was defined in the 90s by these people. And what you do is that you start with a Theorem operator, and acting on 0 forms is the same as the Theorem operator. This operator acting on 1 forms gives you, the Theorem operator now acting on 1 forms gives you a 2-form, and 2 forms decompose again into a 7 and a 14 of G2, and then you project into the 7-dimensional part of that. And that's the D check 1. For the D check 2 of you, again, the Theorem operator on the 2 form gives you a 3-form, and then you project into a singlet. So 3 forms decompose into a singlet, a 7, and a 27, and you project into the singlet. And after that, you get 0. So one can prove that this operator, in fact, squares to 0 if and only if tau2 is 0. And a canonical cohomology is defined, you can define a canonical cohomology for G2 manifolds with G2 structures that have an integral G2 structure, in fact. Okay, so supersymmetry imposes conditions on the structure, on the curvature F of the Young-Mills connection, right? Meaning that F wedge psi is 0. This means F is a 2-form, and that means that F is in the 14 representation. But that is, so I want to call this an instanton. So that is the connection A on the bundle V is an instanton. And one can, again, extend the operator that we had before to an operator, a D-check operator, acting on forms with values on the endomorphisms of V, where dA is the usual covariant derivative for the connection A, right? And alpha is a K-form with values in the endomorphisms of B. And we have, similarly, that this squares to 0, but now, if and only if, Y has an integral G2 structure and F is an instanton. And this, again, leads to cohomology groups for the manifold with values in the endomorphisms of V. Right. So we have a further constraint, right, on the manifold and the bundle, which is the anomaly cancellation condition, which says that the torsion, this torsion that I had before, equals the flux. Right, so this equation is actually it's an equation that mixes all the degrees of freedom of your theory. Right, so it's complicated, but that's life. And there is a further constraint, right? So not only you want supersymmetry solutions, but you also want solutions of the equations of motion. So what you have is that for that to happen, you need to satisfy all the previous conditions, but also this connection theta needs to be an instanton, right? Meaning something analogous to what we had for the bundle before. So in summary, what we have is that a heterotic G2 system is a quadruple, right? That is, where Y is a manifold with an integral G2 structure, V and T have instanton connections, and the anomaly cancellation condition is satisfied, and in such a way that H is the same as the torsion. So now, what we're interested is in the moduli of these equations, right? So in the formations, right? So let's go back to these key ideas. So the first thing we're going to do is to reinterpret the story I just told you, this system as in terms of a differential operator that squares to 0. right? And then we are going to see how the moduli space is related to the first cohomology of that operator. So for that, we consider that linear operator, right? I'm defining there. So, this d theta and dA I have already defined. So this is an operator acting on forms with values in Q, right? Where dA and d theta is defined before, right? And d zeta this is again another covariant derivative with a connection zeta on the tangent bundle with torsion that is minus the torsion that we had before. This is this minus here, right? And it's not an instanton in general, right? It doesn't correspond to an instanton. F and R, so in this previous slide, we have F and R. F and R are linear maps that are defined by this equation. So if M is a K-form with values in the tangent bundle, and alpha is again a K-form with values in the homomorphisms of V, they get mapped into K plus 1 forms, right? But now an M, this form M, this vector valued K-form, gets mapped into a form that has values in the homomorphisms of V by this contraction here. And alpha gets mapped into an object that has values in the tangent bundle by this equation there. Right? So the theorem that we proved is the following. So let Y be a manifold with a G2 structure, phi, be a bundle on Y with connection A, and Ty the tangent bundle on Y with connection theta. Right? So now, and let zeta be the connection 1 form on the tangent bundle that I just defined. Consider the exterior covariant derivative D defined before. Then these projections that are just an extension of the projections that we had before. Then you do the projections on this D, and then you square it, and then you get that is 0 if and only if this is a heterotic system. Right? Of course, that wasn't easy to figure out originally. It took a while. But that's true, right? So I don't have time to really tell you much about the proof. But if you square the differential, right? One way is very easy, right? You see this squares to 0, right? For the heterotic system, as long as the Bianchi identity, that means the exterior derivative on this Bianchi identity of the anomaly, is satisfied. And so it's very easy. So if it is a heterotic system, right, so this is 0, it's very easy to see that this is 0, and this one is 0, and this one is 0. These two are also go very quickly, right? This is satisfied as long as the Bianchi identity, this Bianchi identity is satisfied. So the harder one is this one, right? But this doesn't square to 0, right? And in fact, this one, you need these other terms for it to square to 0, and you need the anomaly for that to happen. The converse is actually harder, right? In fact, the vanishing of the 1-1 entry implies the Bianchi identity of the anomaly, right? So that's the story for the head. So we have this system, right? This system of equations, these heterotic structures. And we have said that we can characterize them by a differential operator acting on a bundle, right? An important operator that acts on a bundle. So now let's study the infinitesimal deformations. So the idea now is of course, you consider deformations of these forms, but the idea is to study the integral G2 structures in terms of vector-valued forms, right? So let me start first with the manifold, of course, right? So one can prove that in fact a generic 3 form can be written in terms of such a matrix, right? In this form, right? So for infinitesimal deformations, when you vary the 4 form, that is Hodge dual to phi, you get here the same matrix M. For higher order deformations, that's not quite true. So now you deform the structure equation that says that you want to have an integrable G2 structure, meaning that this torsion class vanishes. Then you end up with this equation here, right? Something is happening with the battery? I can go on? Okay. Okay, anyway, the formations preserving the integrability of the G2 structure, I mean, it's a computation. Here, of course, it looks mysterious, but it's just a computation varying the structural equations for the integral G2 structure, and you end up with this equation. Again, this insertion operator means that you take, this is a vector value 2 form, and you take the vector index and you contract it with psi. Right? That's what this equation means. And of course, once you do this, you have to consider the trivial, which deformations of these are trivial. So then you discuss diffeomorphisms. You study the diffeomorphisms, and your space of parameters is given by the quotient of the solutions of this equation by the diffeomorphisms. And you get some space, right? That this space tau m0, but it's not general finite dimensional, right? So an exception, of course, is when Y has G2 holonomy, in which in that case this is precisely the first cohomology of this operator, d zeta, and it matches precisely the RAM cohomology that H3, as discussed by Joyce a long time ago. Right? So now let's add the vector bundle, right? So we want to take the formations of the whole the total space of the bundle over the manifold, preserving the structures that we want. And so varying the Instanton equation, right? Again, it's a computation. One finds what's happening. So one finds this equation here, again, another computation, where alpha is a 1 form with values in the endomorphisms of V, and the check does the usual projections. This is the F map that we had before, and meaning because this is a 2-form equation, right? You project into the 7-dimensional representation, right? And this is just so I have to go back on the slides for you to see what F is, right? So this F hat maps a vector valued form, 1 form, say, into a 2 form with values in the endomorphisms of V, which is exact in the dA cohomology. Right? So far we have 2 equations, right, for the deformations of the space and deformations of the bundle, which gives a moduli space of this form, right? So these are the deformations of the bundle, keeping the manifold fixed. And this is a set contained in the moduli space that we discussed before that preserve the Instanton condition, right, by this equation here. And again, there is no reason why this should be finite, right, except in the case in which Y has G2 holonomy. So now we put everything together. Now we remember that we also have the 3 form. We have this extra condition that mixes all the degrees of freedom, and it's a very complicated equation when you vary it. So in this, what we have found is that if you consider the action of D on 1 forms with values in Q, so Z is 1 form with values in Q, right? Now kappa for a 1 form with values in the endomorphisms of Ty, and alpha as before, then the action of D on Z gives you this, right? So these are the equations that we just discussed, right, in the previous slide, the last 2 equations there. When this and this, after you project equals to 0, give you these equations as we had before, right? So this we understand, right? So the claim is that the equations for moduli is that you take this, you do the projection as described, and this equals to 0 gives you the moduli space, right? So the one that is more mysterious is this one, because we said before that the moduli space for the G2 structures is described by this equation. So what happens is that this equation turns out to be the same equation as the one that we had before by the anomaly cancellation, as long, and this is kind of very pretty, right? As long as one identifies the degrees of freedom corresponding to the antisymmetric part of this matrix with the covariant variation of this B field, right? So if you vary the H field, you end up with an equation of this sort. I mean, these two terms are covariant. So the D of B is a covariant term. This is invariant. So you can identify, so this curly B it contains variations of the B field plus other terms, plus alpha prime corrections, right? And but the D of B is an invariant free form, right? So that's very, very pretty. I mean, how all the degrees of freedom are incorporated into these equations. So then the moduli space, the tangent space to the moduli space, infinitesimal deformations, correspond to the first cohomology of this operator with values on Y with values in Q. And we also prove that those forms that are D-check exact correspond to the theorem of B sums of Y and engaged transformations. Moreover, we proved that this is finite dimensional. I mean, we went to a whole story about these operators being elliptic and so on. So this is in fact a finite dimensional space as long as Y is compact, of course. So the summary, so what I have now is that, so this is the main result, what I told you today, right? So we have these heterotic structures, meaning that we are preserving one supersymmetry in space-time. And that corresponds, these are equivalent to some special structure on this bundle Q, right? In particular, we have an operator that is nilpotent. And that infinitesimal moduli space of the heterotic structure with these alpha prime corrections correspond to this first cohomology of this operator, right? So this is an attempt to understand perhaps the massless spectrum. Now, so to finish, I would like to, of course, this is just like a first step in trying to understand heterotic theories. So recently we have obtained the same results from, we constructed a superpotential for these compactifications. And this superpotential, I mean, it's, what we found is that the supersymmetry equations, another way to describe the heterotic structure is to find the critical points of this superpotential. And for the cases for the four-dimensional story, the study of this superpotential was extremely successful to obtain higher order deformations and make an attempt to study the moduli space, have a better understanding of the moduli space. So I think, can I have like 15 seconds? Yeah. So I just want to say in 10 seconds really that, of course, examples and who can compute the cohomologies on examples, I mean, this is all very difficult. And I leave you with a number of, a set of, rather large set of interesting questions that will stem from this. Yeah. Thank you very much.
So, any questions or remarks? No? Thank you again.
Okay.